First, I have a special announcement to read to you from President Machen. Perhaps you saw this. It says, "Attention all University of Florida students and faculty. By order of the Office of the President, summer term has been extended for 2 weeks." Didn't you see that? So these statements you have on the board are incorrect. All right, 3 weeks. You don't like that announcement, huh? I'll be here. Why can't you be here? Key to bonus quiz 3 is posted. There is, of course, information on there regarding transition metal complexes. So you may benefit by looking at this key. As you know, part 2 of our last exam is this evening. Location this time is Turlington, LO11, 7 to 10 p.m. And for those of you who are interested, and I hope that many of you are, perhaps all of you, after we finish grading, exam 4 and bonus quiz 3, like all the other exams and bonus quizzes, are your property. So if you want to see me to get this stuff, have your records for this gathering complete, please do so. Next week, or any time thereafter. You know, if, for example, following this week you're heading back home and home is not Gainesville, when you come back this fall, if you're interested, see me. And you can have this stuff back. Now then, a couple of additional theoretical considerations. I trust that you will recall we started this stuff at the tail end of chapter 23. When we talked about nickel tetracarbonyl and used our discussion of such as a springboard into what we've been talking about in chapter 24. Now, the best theory we have presently available, we're talking about important properties of complexes, as with any material, structure and bonding, is ligand field theory, modified from a molecular orbital standpoint. This is pretty sophisticated stuff. I would like to have some time to talk about such, but such is not available. If you go on and study more chemistry, say for example a junior level or senior level course in inorganic chemistry, which we have here, Chemistry 3610, I'm sure you'll hear about this stuff. What you discover with this far better theory that I just mentioned, but we're not going to talk about it, is that it has to be realized that when we have a complex of a particular geometry, and all the complexes have particular geometries, most common is octahedral, but square planar complexes of course exist, tetrahedral complexes exist, trigonal bipyramidal complexes exist, and geometries, other geometries also exist. That when a particular complex geometry is developed, the d orbitals, the valence d orbitals of the complex transition metal are no longer equal in energy. This gives us a springboard into recognizing ways by which bonding and structure can be explained far better than what we can do with valence bond theory, which is the theory we have so far looked at. I don't know if you've heard the term valence bond theory as such, but all valence bond theory is hybrid theory. Same thing. Okay? And that's what we did at the end of chapter 23. When we talked about nickel tetracarbonyl, we recognized how it could be argued that the nickel atom in that stuff was sp3 hybridized and the complex geometry was tetrahedral. And then we talked about other unusual but stable complexes, unusual by way of the fact that the complex metal was in an unusually low oxidation state. I could get a handle on the existence of such by counting electrons, 18, the magic number of electrons, so that the metal in the complex could be considered isoelectronic with krypton for the valence state. Now that gadget, counting valence electrons, does not apply to common complexes where we find metals in positive oxidation states, which are of course the most common oxidation states exhibited by metals in their chemistry. Well, some of the complexes we'll consider today. The 18 electron krypton analogy will not apply, because these complexes that we will look at today will not be complexes of metals in unusually low oxidation states. So don't apply that rule. Then, at the end of chapter 23, we also argued how and why we can realize that a stable complex of a metal in an unusually low oxidation state can show sp3 or dsp3 or d2sp3 hybridization for the complex metal. Because all of those types of hybridization, which correspond to tetrahedral, trigonal, bipyramidal, and octahedral geometry respectively, would show electron configurations, valence electron configurations for the complex metal for which we counted up 18 electrons. But in so doing, we recognized that square planar geometry is not a possible geometry for a transition metal complex in or containing the metal in an unusually low oxidation state. So, we'll now extend some of those considerations, valence bond considerations, where we will try to identify hybridization for the metal and corresponding geometry for the complex, by paying attention to properties of the complex such as magnetic character, of which there are two types. Diamagnetic, all the valence orbitals for the metal in the complex are filled or empty. No half-filled orbitals. Did I say that right? Let's say diamagnetic, paramagnetic, as opposed to paramagnetic, where one or more of the valence orbitals for the metal in the complex is half-filled. Tetrachloronickelate, an anionic complex. Again, I don't care about its name. Its formula is far more important. This is a complex of nickel in nickel's most common oxidation state in its chemistry. What is the oxidation state for nickel in this material? +2. Each chloride ion ligand is -1. The charge on the overall complex is -2. Upshot, +2. Oxidation state for the nickel, added to 4 times -1 for the 4 chloride ion ligands, gives us -2 as the charge for the complex. This is maximally paramagnetic. That being the case, can we write the valence electron configuration diagram for this complex? Sure we can. Let's make some space over here and get at this. For a transition metal, any transition metal, and you start by realizing, as we've already noted, what intensifies the chemistry of these elements is the fact that they have a mixed bag of valence electrons, D and S, where the D valence electrons are from one lower energy level than the S valence electrons. For period 4, which is first row transition metals, the valence electrons are 3d and 4s. Period 5, 4d and 5s. Period 6, 5d and 6s. So, when you're going to write electron configuration diagrams, which we remind you is an energy diagram, we'll start with the occupied inner d orbitals. For period 4, this will be 3d, since we're talking about a nickel complex, which is from period 4. Then in terms of relative energies, after 3d, 4s, then 4p, and possibly 4d. Now, for the period 4 transition metals, for the element itself, not for the complexed metal, will any of the 4d orbitals be occupied for the element itself? Are any of the 4p orbitals occupied for the element itself, for the transition metals, period 4? Yes or no? No. The mixed bag of valence electrons are all 3d, 4s. Nickel is atomic number 28. That means 10 valence electrons for the element. Here we have nickel plus 2. So the complex nickel ion in this stuff has how many valence electrons? 8. And each chloride ion ligand supplies 2 additional electrons, a non-bonding pair per ligand, which becomes a bonding pair as complexation takes place. Well, if this complex is maximally paramagnetic, we can start by writing this as the 3D configuration. Because we got 8 d electrons for the metal, and the only other possible arrangement of these 8 electrons in the 3D sublevel would correspond to diamagnetic character. So what orbitals are occupied by the 4 ligand non-bonding pairs, which on so doing, which on occupying these orbitals, become bonding electron pairs? This, this, this. So for this, which we know is maximally paramagnetic, so we've written an electron configuration which corresponds to such, we find or expect nickel to be sp3 hybridized, which means we expect the geometry of this thing to be what? Tetrahedral. Now this is strictly a theoretical consideration, but this we can find by studying structure and geometry in the laboratory with appropriate methods. And we find this thing is not only maximally paramagnetic, which is a property that we started with to get at this, we also find this stuff is tetrahedral. All right? So that takes care of this complex. Now, tetracyanonickelate. This one is diamagnetic. But notice that for this complex, we have 4 ligands like we have here, and each of these ligands is monodentate. So we are recognizing that 4 non-bonding pairs, 1 from each monodentate ligand, will be supplied to the valence electron environment and create 4 bonding pairs, sigma bonding pairs, just like we had for this stuff. And this also has the metal in the same oxidation state, plus 2. But the d electron configuration can't be this, because this stuff is diamagnetic. So it must be this. It's the only other possibility. And now, when we recognize the empty orbitals, that are part of the valence environment of the complex nickel ion, the empty orbitals which will be available for adding, so to speak, 4 non-bonding pairs from each of 4 monodentate cyanide ligands. We now got an empty 3d orbital. So, instead of sp3 hybridization, we now have dsp2 hybridization. Do you recall the geometry to which this hybridization corresponds? Square or square planar? Now, on recognizing this to be the electron configuration for this complex, we can answer questions like, is cyanide ion or chloride ion? The stronger ligand? Which one appears to make stronger coordinate covalent bonds with the nickel in the +2 oxidation state? Chloride ion or cyanide ion? What would you say? Well, we'll give you the right vote. That's cyanide ion. But if I ask you a question like this and all you put down is the right vote, you so far have earned nothing. And I don't give a damn about votes. Just like you didn't give a damn about President Machen's message. Defend the vote, chemistry students.
Well, just based on the fact that it's diamagnetic, it should be more stable.
Why?
Because electrons like to be paired.
Is elemental oxygen stable?
Yes.
Is it paramagnetic?
Yes. I mean, that's an example, but like, it's not set in stone, it's just...
Do you believe that each and every atom of each and every element which has got an odd atomic number is paramagnetic? You don't believe that?
I believe that.
You believe that. Are you going to take then the periodic table and tell me that every element with an odd atomic number is not very stable? I don't think you'd tell me that. So you better go someplace else with this argument. The stability resolution is what we're trying to get at, but it hasn't got to do with magnetic character.
I was going to say often ligand strength is based off its like base strength. And it's
be careful.
Much better.
The base strength analogy tends to work if and only if the ligand is strictly a sigma bonder. Neither of these ligands are strictly sigma bonders. More on that in a moment. Let the facts talk to you. You're jumping past what I would hope is obvious, but that's okay. Because one of the things that you are trying to learn how to do in this gathering is to recognize what's obvious. Chloride ion ligands. They made bonds on complexing nickel strictly in what energy level? How about cyanide ligands? Did they muscle in energy level number 3? Would you believe that if cyanide can get a bond, can get a non-bonding pair to become a bonding pair in energy level number 3, that these electrons are certainly closer to the nucleus of nickel ion and therefore will be attracted more strongly? How about that? It's not a fancy argument. We're just looking at the difference in valence level occupation by the incoming ligands. Now, we can talk about other properties of cyanide ion versus chloride ion. I mean, questions of this nature I feel totally at liberty to ask about at this stage of the game, because we've been through this stuff. On what basis would you argue that this is a stronger sigma bonder than this? I'll give you a clue. A comment that was registered earlier relates to this. Because sigma bonding strength, as opposed to overall bond strength formation tendency, sigma bonding strength does relate to Bronsted basicity. Now, cyanide ion is not a strong Bronsted base, but it's stronger than water. A good deal stronger than water. Whereas chloride ion is such a weak Bronsted base, it's weaker than water. So we know that cyanide ion is a much stronger Bronsted base than chloride ion. On that basis, we could well expect cyanide ion to make much stronger sigma bonds than chloride ion. Does that seem to keep with other properties that we can explain from a theoretical standpoint? Now, let's do this just so you don't think this is a chlorine atom sticking over here. Why would you expect this non-bonding pair to be more readily available in bonding than any of these four non-bonding pairs on the chloride ion? Because we've recognized the strength of a ligand to make a sigma bond has got nothing to do with the number of non-bonding pairs it has. Depends on how available the material can make these non-bonding pairs for bonding.
Electronegativity.
Carry on.
Chlorine is 3.0 and carbon is 2.5.
Well, that's good enough. The donor atom is of lower electronegativity for cyanide ion. Now, could we offer an argument also based on charge density from a charge to size ratio standpoint? What argument would we offer now? I'm looking at two species, one which shows a negative charge on chloride ion, the other one which shows a negative formal charge. The whole thing is minus, but it's got the formal charge of -1 is on carbon. Is carbon a good deal smaller than chlorine? Is it not? From size trend considerations? Would that not argue for the charge density of this atom being greater than the negative charge density of this atom? Hey, that fits the facts. Fits the facts, we'll use the argument. Okay? Stuff like that. Okay? So now we got a handle on explaining why, just from comparing these two complexes and their properties of magnetism, one paramagnet, the other one diamag, how we can argue that cyanide ion is a stronger ligand than chloride ion. Next question. Can these ligands make pi bonds? Can these ligands make pi bonds? Are these ligands pi bonders, or at least potential pi bonders? In order for a ligand to be capable of pi bond formation at a coordinate covalent bond site, at the minimum, what property must this ligand exhibit? I'm listening. What? Remember way back to nickel tetracarbonyl? We went into a long argument about nickel tetracarbonyl, a long argument to support the conclusion that the stability of that complex cannot possibly be rationalized from a sigma bond strength standpoint. It has to be rationalized from a pi bond strength standpoint. That led us to talk about carbon monoxide as a ligand to the extent of saying, how can this thing be a pi bonder? Now, we did take a look at the molecular orbital diagram for carbon monoxide that you see in chapter 25 of the notes. But without even taking that look, on what basis could you argue that carbon monoxide or cyanide ion in this case are potential pi bonding ligands?
Does that have to do with role reversal? Or it's cyanide?
Well, now you're just talking about the mechanism of pi bond formation. I'm talking about the ligands themselves, cyanide ion, carbon monoxide. What examination did we make of these ligands to argue that yes, they have the capacity to pi bond? You remember taking a look at their Lewis structures and actually recognize a shortcoming of Lewis structures? What do Lewis structures show you? What do they not show you? That's right. They don't show you all the valence orbitals. But a little bit of counting will allow you to recognize how many valence orbitals you got. Well, N from period 2, C from period 2. Each has 4 atomic orbitals. 4 plus 4. That means this thing has got 8 molecular orbitals. Because if you bring the atoms together, the atomic valence orbitals combine with each other to make molecular orbitals. Valence orbitals which no longer belong to this atom or that atom. They belong simultaneously to each component atom of the species. That's why they're called molecular orbitals. They belong to the molecule itself. Of course, this is an ionic molecule, but so what? Well, this picture shows us occupancy of how many of these 8 molecular orbitals? 1, 2, 3, 4, 5. Hey, there's 3 more there. And then when we took a look at the diagram that you see in chapter 25, which is on molecular orbital theory, you recognize that these empty MOs are in fact capable of pi bond formation. So this is a pi bonder. This a pi bonder? Chloride ion? Hey, there's something else you've talked about previously. This stuff pretty stable? Is this stuff pretty stable? You're damn right it is. Now then, is this stuff pretty stable?
More so than it is.
Now, you investigated each of these in 46 laboratories. Assignment 6. What did your investigations that you did this term, for those of you who are in laboratory this term, and that's most of you at least, what did the results of your investigation suggest to you about which of these is more stable? And I'm sure Mosen discussed this stuff with you because it's a very important part of chapter 19. Now, I was at that time lollygagging in Vietnam, probably with my wife's nephew playing pool. I like to shoot pool. I don't like the fact that most pool shooters smoke cigarettes like wild. And in Vietnam, you can smoke cigarettes any damn place you want. I don't like that. At the end of chapter 19, regarding work that you did in class, you found this stuff is a hell of a lot more stable than this stuff. Yet we've already recognized that ammonia, from a sigma bond former, the strength of sigma bond formation, ammonia beats the hell out of chloride ion. If you have ammonia and chloride ion competing for H+, hey, chloride ion doesn't get in the game, doesn't even get in the game with water. But when you turn this into Lewis acid-base chemistry rather than Bronsted-Lowry acid-base chemistry, chloride ion beats ammonia, at least when it comes to silver ion. So are you going to tell me the stability of this, which exceeds the stability of this, is a consequence of strength of sigma bond here? How about this? Is this stuff pretty soluble in water? Is this stuff pretty soluble in water? Would you bet this compound is ionic? Because if this compound is ionic, it ought to be water soluble. That compound is quite soluble in water. How does the positive charge density of Ag plus compare to the positive charge density of Na plus? How much the positive charge densities of these ions compare? They're both +1. Which is much larger? You know the answer to this. This thing is Ne configuration. This isn't noble gas. This is a hell of a lot bigger ion than this. So the positive charge density of this is very small compared to the positive charge density of this. That means if this stuff is ionic, the silver ion, chloride ion attractions for each other from a Coulombic standpoint are guaranteed to be weaker than the attractions of sodium ion for chloride ion. That means if this stuff is ionic, this lattice is going to come apart more readily in water than this lattice does. Well, we know that's not true. This stuff is readily soluble in water, not this stuff. That's telling us something. Think this is ionic? It isn't. What would you do to find out? Now you know this is ionic, at least principally so. I give you a sample of silver chloride. I give you a sample of sodium chloride. Your job is to tell me by experiment. Confirm that by experiment. Sodium chloride is quite ionic in character where silver chloride is not. What will you do? We talked about this before. Now apply it.
Conductivity.
Well, tell me what you're going to do.
I dissolve it in water.
Wait a minute. You dissolve something in water, you might make ions. Hydrogen chloride is molecular. You dissolve hydrogen chloride in water, you're going to make ions all over the place. Are you going to conclude from that hydrogen chloride's ionic? No. So what are you going to do? You got to refine this investigation. Don't make water solution. You got to investigate the pure stuff itself. Under what conditions? Melt it. You're damn right. You melt this, you find out it's a marvelous conductor. You melt this, you find out it's a feeble conductor at best. All right, you're finding out this stuff isn't very ionic at all. It's telling you, if a melt of this is a very lousy conductor, do you think that in the melt you got silver ions and chloride ions swimming around? Or do you think that in the melt, because this melt is not a very good conductor at all, that for the most part you got silver chloride molecules swimming around? How about that? You gotta let these facts talk to you. That's where you really get the handle on this stuff. Consider their properties and then say, what the hell does all this stuff mean? And the tee-off that you have on this is your knowledge that this is not very soluble in water, whereas that is. That's the tee-off. That's got to set your mind to thinking. How can this be? All right? So we're now recognizing stability of this is attributable to pi bonding. Like nickel tetracarbonyl. That guarantees that this is a pi bonder. How can this be a pi bonder? Here's two ions. Oxide ion, isoelectronic with neon. Chloride ion, isoelectronic with argon. This is a pi bonder? We found this is a pi bonder. Now tell me from an explanation standpoint why this is a pi bonder. Because in order for a species to be a pi bonder, it's got to have, for the model we've cast, where the coordinate covalent bond site, now it's role reversal, the metal supplies the d electrons, because you can't make pi bonds with s electrons, and metal's only got s and d valence electrons, doesn't have p valence electrons. Okay. And ligand supplies one or more empty orbitals. Okay? We've already recognized such for cyanide ion. How can you recognize chloride ions got empty valence orbitals which are capable of pi bond formation?
Structure.
Well, what structure?
Lewis.
Electron structure. Chloride ion comes from chlorine. That's an atomic number of period 3, isn't it? What's the total valence electron capacity for period 3 atoms? We did this before. 18! How about that? Hey! You see that picture? That shows chloride ion with 8 valence electrons. That means it's got space for 10 more. Why? What valence orbitals does this thing have which are not occupied? D orbitals, you betcha. They're all there, the whole complement of D orbitals. I bought some D orbital models today. 4 of the 5 d orbitals look just like this. Except that 3 of the 5 d orbitals, which each look like these three-dimensional four-leaf clovers, 3 of the 5 d orbitals have the d orbital lobes between the axes. This has its orbitals in this plane, this one, this plane, and then the remaining one in this plane. This d orbital looks just like that d orbital, except that this is the x squared minus y squared d orbital, which we took a look at previously in the notes, because there's a picture of d orbitals on page 2430. Okay? This one has the orbital lobe skewered right by the axes. So when we trumped up a hybridization scheme for a square planar complex, like, I erased it. The tetracyanonickelate complex, which is square planar. Hey, the d orbital, which is part of that dsp2 hybrid, is this thing. If we imagine that the complex is contained as a square in the xy plane with the orbital lobes lying on the axes, x and y axis respectively. Because this thing is in the xy plane. Remember, for chemistry, this is the y direction. X direction, up and down, z direction, okay? So this thing's in the xy plane, and this is the the y-axis, and this is the x-axis. So, both of these are pi bonders. But this is a better sigma bonder. So now we got information to allow us to understand what the heck's going on here. In any case, what we have now also talked about was question 2445, which in the notes reminds you about the dsp2 hybrid and the valence orbitals which are used to create this hybrid. Well, we had the diagram still here. This is 3d x squared minus y squared, simply because to make the problem as geometrically tenable as possible, we're going to argue that this tetracyanonickelate complex, which is square planar, lies in the xy plane. Get on there. and has the ligands lying on the X and Y axis respectively. So here is Cn minus, here's Cn minus, here's Cn minus, here's Cn minus. I've drawn it like this because the bonding is through the carbon end of the cyanide ion ligand. Here's nickel 2. And so we've recognized that the p orbitals which are used will be the 4px and 4py orbitals respectively. Because those are the p orbitals which lie on the x and y axis respectively and are in the xy plane. Okay, once I decide what plane contains this complex, by default that tells me what orbitals I'm going to use to form the hybrid. It's not fancy. That's all there is to it. We're just letting this thing talk to us again. Now, one more question on this. Have we not discussed that for pi bonding to be effective, what overall shape would we prefer for the species in question?
Square.
Well, it doesn't have to be square.
Or just planar.
Planar, that's right. So we can get all these orbital lobes, which are going to overlap with each other to make the pi system, parallel oriented in space. Parallelly, that's a new word. Parallel orientation in space. That way we get the appropriate side-by-side overlap of p orbital with p orbital to make pi bond. And with the models that we have, now we can see how a d orbital can make a pi bond. P orbital approaches this way. We've drawn this picture before. There's this thing. There's a pi bond formed by overlap of a d orbital with a p orbital. There's the d orbital. You know, the p orbitals all look like these. What do you want to call them? Three-dimensional figure eights? Weightlifters, dumbbells, whatever. One more comment on the d orbital, since we've talked in brief about them at this stage of the game. When you look at the d orbital pictures, oftentimes students say, this one looks funny. This is a dz squared orbital. Looks funny because its model is obviously different from the other models, shape-wise. Again, 4 of the 5 look like these three-dimensional four-leaf clovers. Okay? What this looks like is a p orbital. Here's a p orbital on the z-axis. That has a donut for a belly band. Okay? I like to call it a cummerbund. Boys who don't know about cummerbunds usually are required to learn about cummerbunds when they engage in this activity called nuptialization. Because the bride-to-be insists that you will be appropriately attired and you will wear a cummerbund. Because they're nice and attractive, right? This fancy belly band that goes around a tuxedo at the waist. So this d orbital has a cummerbund. Now, from a geometry standpoint, this is called a torus. T-O-R-U-S. All right? Now, let's show you a trick. Because, independent of what the models of the orbitals look like, each orbital from a given sublevel, like all the 3D orbitals in the 3D sublevel, of which there are 5, they're all equal electron density probability diagrams. They're all equal. See what this thing looks like? Here again is our x squared minus y squared orbital. Okay? If I hold it like this. The square designation means that the axes penetrate the heart of the lobes. And the xy designates that the lobes are contained in the xy plane. All right? See this thing? Let's hold this, the orbital, this way. Okay? You see the p orbital part? Now watch how this torus is generated when I do this. How about that? Now I've created the belly band. Really? These are equivalent electron density probability functions. They're equivalent. And this is one way you can see it. Because when I play this game, I generate the torus. There's the p orbital, the part that looks like the p orbital, and there's the torus. Okay? I only have one more question on this stuff. Question 2446. The question is, well, let's look at the question in the notes. Can complexes of nickel-2. Okay. We've just looked at dsp2 hybridization for nickel-2 in the square planar tetracyanonickelate complex. Okay? And talked about why pi bonding is expectedly stronger for that complex compared to the tetrachloronickelate complex, because tetracyanonickelate is square planar. So you got all this appropriate orientation of lobes. Now then, can nickel-2 be hyb for hybridized D2sp3 for its octa for octahedral complexes? You have, for example, been asked to recognize that platinum-4 can be inner orbital or outer orbital hybridized. Platinum-4, this is a case you looked at during discussion class. Complex with chloride ion, hexachloroplatinate 4, platinate because it's an anionic complex, but platinum's in a +4 oxidation state. This is outer orbital. It's sp3d2 hyb versus this is inner orb D2 sp3 hybridized. And now we've got reasons to argue why this is the case. This is a much stronger sigma bond former than chloride ion. Okay? So, this muscles its way into inside valence d orbitals. Not these guys, they're not strong enough. Like the chloride ion, cyanide ion situation we just looked at for the nickel complexes. So there's our question. Can nickel 2 be hybridized D2sp3 for its octahedral complexes? Is this possible? Is it possible? All right, we'll tell you the vote. It ain't possible. Now tell me why it ain't possible. Nickel 2. How many valence d electrons is nickel in the plus 2 oxidation they'd have? 8. Well then, if I got 8 electrons occupying the 3d orbital, how can I make available 2 of these 3d orbitals for D2 hybridization? I can't do that. Right? Nickel 2's got too many valence electrons. Okay? Now, a little bit of practice. Since we got a question like this on the last exam. I mean tonight. This is from multiple choice format exam, which unfortunately is the format that this university forces me to use in spring and fall. Because to try to give real exams like you folks have had during the long terms, I can't get the time. What do I want to do, being the crazy man that I am? I want to give students exams on Sunday afternoons. Seriously. I give you 3 hours, 4 hours, I don't care. There's no problem parking here. You can't use Saturdays, that's impossible. You can't get close to this place on a football Saturday, for example. That's impossible. Yet this damn dumb place told me to run Saturday laboratory classes a few years ago in the fall, and we had a fit. I tried to get them to understand that this is totally stupid. It didn't matter. Once the administration decides, they don't give a damn what people like I have to go through. People like me have to go through. I'm the guy in the trench. I'm the guy that makes it work. But do they care about the problems I have? Hell no. They don't. Decisions are made like this without any interaction with me whatsoever, and I'm the guy that has to do the job. I resent that. I mean, I resent that passionately. Back to this multiple choice exam. Because I'll tell you the truth. If you think multiple choice exams are fair, you are dead wrong. At least with the types of exams you've had this term. You put me in the position, or our team, where we have to evaluate what you've done. Multiple choice exam, you got to evaluate me. That's backwards. You're not in position to do the evaluation. You're just learning. And when all you do is bubble in a circle, even if you got bubbled in the right circle, I got no idea if you know what's going on. You haven't provided me with any indication whatsoever of your understanding or lack thereof of the question which was asked. Multiple choice exams, if I ran this university, multiple choice exams would be outlawed. And exams would be given on Sunday afternoons. I mean it. This place is an educational institution. We should do everything possible to make the educational process as viable and as easy to run as it can be. That's why this place is here. It's not here for football, and it was never built to support research. Now, research is a marvelous activity. But when research gets all the considerations and the educational process gets kicked in the pants, people like me object. And you're the ones who should object. Really, passionately. Because you're here for an education, I hope. In any case, enough of that sermon. I'm going to write 5 complexes on the board. And then we'll ask a question. 5 complexes of cobalt, all with the same ligands. But notice that for a type of ligand, the number of such can vary as we go from complex to complex, or does vary as we go from complex to complex in some cases. And also notice that the oxidation state of cobalt is not the same for each complex that's listed here. Okay? Question. Treat with excess ethylene diamine in solution. I'm going to make a water solution of each of these complexes. Because of the chelate effect, every one of these will convert to this. Two plus for the complexes which have cobalt in the +2 oxidation state. Or 3 plus for the complexes of these which have cobalt in the +3 oxidation state. Okay? We finally get to the question. Which complex reacts with largest delta S0 and smallest delta H0? Now, for starters, you think there's going to be any change in consequence of, or any difference of consequence between delta S0 for these things?
Yes.
On what basis?
Electron count.
What is that?
Electron count.
Electron count.
Yeah.
Well, I don't know what you mean by electron count.
Some of those things pi bond, and the strength of pi bonds depends on the total number of electrons.
No, there's not going to be any pi bonding here to speak of.
Isn't it just like number of moles?
Mm-hmm. Principally number of moles.
So you start with 1 mole of that entire compound, and when you treat it with EN and it dissociates, you have, like, for example, for the first one, you're going to have 2 moles of ammonia, 2 moles of water.
Yeah. When I react this with excess ethylene diamine, I'm going to put in solution 2 moles of this, 2 moles of this, okay? And 2 moles of this. Okay? Here, 2 moles of this, 1 mole of this, 3 mole of this. And you know how to just go on down the list. Okay? Do you think there's much difference in delta S0 for each of these reactions? No. But how about delta H0? Now, delta H0 is talking about what? Bond strengths. Okay? Now then, here, I will replace 2 ammonia molecules in the first coordination sphere with 1 ethylene diamine molecule, and there's practically no change in delta H for that. Because ammonia and ethylene diamine are very similar in sigma bond formation strength. So my payoff here will be in making much stronger bonds, ethylene diamine, compared to the coordinated water molecules and the chloride ions. All right? Now what about fluoride ion versus water? You think fluoride ion or chloride ion makes a stronger sigma bond? Let's put up here. Neglect pi bonding. What do you think? Fluoride ion or chloride ion? Stronger sigma bonder? Fluoride. In sigma bonding, you could take a look at Bronsted base strength. Fluoride ion, of course, is a much stronger base than chloride ion. All right? Now then, notice that for this complex, and this complex, and this complex, I am removing 2 moles of ammonia from the first coordination sphere. Okay? But here I'm removing 3 moles, and here I'm removing 3 moles. Right? So do you think it's a good bet that the least favorable change in delta H 0 will be with complex 3 or complex 5? Because I'm not getting much delta H payoff when I replace an ammonia molecule with ethylene diamine. Well, here and here I'm replacing 3 moles. Whereas for all the rest I'm replacing 2 moles. And making much stronger bonds when I knock out water, chloride, even fluoride ion. So, what decision can I reach between 3 and 5? Remember, we're looking for the least favorable change in delta H. On what basis? Well, let's make this easier. I'll put in chloride here. Notice that these 2 complexes are now compositionally identical, aren't they? With 3 or 5, with 3 or 5, 3 or 5, will I get the least favorable increase in bond strength? All of these are going to result in an increase in bond strength. 3, 5. What's the difference between 3 and 5? What is that? Oxidation state of cobalt. This is cobalt 3. This is cobalt 2. Tell me, with which of these cobalts are you going to make the stronger sigma bonds? Which one? Come on, Coulomb. If you're something with negative charge density, are you going to stick more strongly to this or this? This! This is more plus. Well, the answer is 5. Any questions on this? In retrospect, I don't even know why I put the delta S part up there. Should have just focused on delta H. Because delta S is about the same for all of these things. Okay? So, I like to leave gatherings with a little bit of organic chemistry. Benzene ring. Obeys Huckel's rule. You know about Huckel's rule. Stuff like that. Okay? So let's imagine that after you all make wonderful scores and strong A's and all that good stuff, that you, in preparation for organic chemistry, take your benzene ring and treat it with a drink that contains this stuff, sucrose. Some people like sugar-flavored drinks. Be careful though. Because some people prefer drinks containing this stuff. This is ethanol. The active ingredient in beer, wine, vodka, stuff like that. But remember, you've all done well, so you're going to take this benzene ring and you're going to treat it with which of these is your favorite drink. And so you can make the benzene ring be like this. And that's it.